Hello and welcome back, everybody. Today's topic for 10.5 is surface area and volume. For some reason I put in the title prisms and pyramids, but we're also going to be looking at spheres, which is neither of those. Basically what we're going to be looking at is surface area and volume, which pertains to three-dimensional figures. So our focus before this was with two-dimensional figures. So two-dimensional figures are flat. We can draw them on a piece of paper without any issue. If we're looking at a three-dimensional figure, it's a little harder to draw on paper because a 3D figure has a depth to it, and it occupies 3 dimensions of space. So three-dimensional figures have depth. There's that third dimension. So a little, like, they can obviously still be drawn on paper, but you sort of have to create the illusion that there's depth in the figure. So a 2D might, you might be looking at something like a square with a height and a length, or you could say length and width. And then for the 3D figure, you have the length and the height and the width. So 3 separate dimensions. You've got, a vertical or horizontal, and then one that either shoots back or forward, however you're looking at that. Okay, so I have some examples of common three-dimensional figures that we see. The sphere, the cube, the cuboid. That's kind of a funny word. I don't ever use that word, to be honest with you. It's correct, but I like to prefer to call this a rectangular prism. So a cuboid can also be referred to as a rectangular prism. I prefer that name. Cuboid just sounds weird, but that's my opinion. A cylinder, and we have a hexagonal prism. We've got a cone, the square-based pyramid, a triangle-based pyramid, triangular prism. So what is the difference between that word prism and the word pyramid? Now, when you say pyramid, or when I say pyramid, you probably have a thought in mind, and there's a couple pictures there for you, but you see the point happening there. The cone is also technically an example of a pyramid. When you're looking at a three-dimensional figure with just one base, we call that a pyramid. And then if you have two parallel and congruent bases, we call it a prism. So on the cube, for instance, you have like the front and the back, those two parallel congruent bases, or you could also say the top and the bottom would make that a prism. So this would be a prism. This again has two parallel congruent bases. You can say the top and the bottom, and this would also be a prism. Oops, I did not mean to erase my word there. The cylinder is technically a prism. It's got these two circular bases, and a hexagonal prism, two hexagons for bases. And then we have this triangular prism where you have these two triangular bases. And then if you have a pyramid, you've got just one base. So the cone just has one base. The square pyramid, the triangle pyramid, those are all pyramids, right? So if a 3D figure has two parallel and congruent bases, we call it a prism. And then if it's just got the one base, we call it a pyramid. Now, not every three-dimensional figure fits into one of those categories. Like the sphere, for instance, isn't a prism or a pyramid. It doesn't have any bases. It's just a sphere, okay? So the first concept we're going to look at with these 3D figures is surface area. Now, its area, like we talked about before, but because a 3D figure now encloses an amount of space, if we were to find the area of each of the surfaces and combine all of those, we would get the total surface area for our 3D figure. So the surface area of a 3D figure is the total area for each of its surfaces. So each of the surfaces that are used to enclose it. And there are formulas for different figures, but I really just want you to have an understanding of surface area, and I think the most effective way to see it or to calculate it is to visualize what we call the net of the 3D figure. That is, if we were to flatten the 3D figure out, if we were to take apart all of the surfaces and lay them out flat, what would it look like? So this is an example here of a rectangular prism, right, where we've got this top piece and bottom piece, right? We have the side here and this corresponding side here, and then you have, it's going to be hard if I color all of this, but you have the front of the prism, and then you have the back of the prism, right? So you have like sets of pieces that correspond, okay? So let me just, that was just going to get too messy. If we were to take this apart, surface by surface, and lay it out as a flat 2D figure, what would it look like? Where would the pieces go? So let's say we wanted to identify where in this is, come on, this is what we would call the net figure here of that rectangular prism. We have the top and bottom piece. Let me just highlight them here. So the top and bottom piece are the 2 by 3 pieces. That would be this piece here and this piece here. Okay, so you've got the top and the bottom. There they are if they were flat. We've got the rectangle at the top, the rectangle in the bottom. Okay, and then I'm gonna have to get rid of all those because it's just gonna be too much. If we were to look at the sides, so let's say we wanted the side here, this side here, which corresponds with this side here. Those sides are 2 centimeters by 6 centimeters. So the 2 by 6 portions, 2 by 6 portions would be these pieces here, right? So there's 2 rectangles there. And then lastly, we have, went too far. Let's see, we've got the top and bottom. I did the side pieces, now we need the front and the back. So we have got the front here, right? We also have the back here, and those pieces are 3 by 6, and the 3 by 6 pieces would be here and here. Okay, so basically you took this thing apart, it's 6 separate rectangles, and if you fold them up, they all together make that rectangular prism. So if I wanted the surface area, I would just find the area for each of those 6 rectangles that make that prism, and then add them all together, okay? And the same thing would work for any 3-dimensional figure. So just so you can see it again, this is a square pyramid. Right, it's a pyramid, it's got one base, and that base is a square, so we would call it a square pyramid. And then this would be the net for that square pyramid. If you were to unfold it, if you got these triangular sides here, right, these 4 triangular sides, that's what you're seeing happening here. And then of course you have the base, right, the square base, and that would be this piece here. So if you were to fold it out, we've got the 4 triangular sides, we've got the square base on the bottom. If you found the area for the 4 different triangles and then found the area for the square and added those 5 areas together, you would get the surface area for that figure. Okay, I can't leave this, it just looks horrible. Sorry if you're marking up your papers. Okay, so let's try this out. If we wanted to find the area here, if you want to try to draw the net, you can. If you want to just separate, I like to label like the front here is going to have also a corresponding back piece. So first I'm going to do the front and back. Okay, so the front and back are both 5 by 2. So I have a 5 by 2 in the front. I have a 5 by why did I do that? A 5 by 2 in the front, and I have a 5 by 2 in the back, right? That's a rectangle. So when I say 5 by 2, I mean length times width to find the area for that front, and length times width to find the area for the back. So I have 10 there, and I have 10 there. So for the front and back, we're looking at 20 centimeters squared. Okay, and let me just call this a 1. And then we have, let's say, the top and the bottom. Okay, the top and the bottom. 2. Top and bottom are going to match, right? They're going to be the same rectangle, and the dimensions for that rectangle are going to be the 8 centimeters here and the 2 centimeters here. So 8 by 2 and another 8 by 2. So that's going to be 16 and 16, which gives me 32 centimeters squared there. And then lastly, got the sides. So the sides here, let's call that 3. So the sides, we've got 2 of them, left side, right side, if you want to call them. In either case, the dimensions are 8 centimeters by 5 centimeters. So 8 by 5 and another 8 by 5. So we've got 40 plus 40, which is going to be 80 centimeters squared. So now if we add all of those together, the total area of all of those surfaces, we have our surface area. So the surface area, which I'll just call SA, is going to be 20 plus 32 plus 80, which is going to be 132 centimeters squared. Okay, so there it is. not too difficult. Just make sure you organize your work and you'll be fine. The only mistakes I see on this one are repeating lengths, like not separating the front and the back versus the top and the bottom or something like that. So if you label what you're looking at, just make sure you're getting those surfaces twice if it's a rectangular prism, and I think you should be fine. Okay, so I'm going to show you on the next one a little more shape that's a little more irregular, like this. Okay, what would all of these surfaces look like? So first of all, prism or pyramid? Hopefully you're answering. I wish I could hear you. This is going to be a prism because we have two bases, and the bases here happen to be these trapezoids. So you might be thinking, shouldn't the base be on the bottom? But the bases are considered the parallel and congruent sides. So we have two parallel and congruent pieces here, so those are considered our bases, okay? So this is technically classified, since those bases are trapezoids, we would call this a trapezoidal, that's a fun word, a trapezoidal prism, okay? But I'm going to do the same approach here to find the total surface area. I'm going to start with my trapezoids. So I've got one here, I've got the same one in the back. So I have the, I'm going to call it the front and the back. Front and back. And so area for a trapezoid is 1/2 times the height. And we can see right here that the height for our trapezoid is 4. So 1/2 times the height of 4 times its base 1 and base 2 of our trapezoids, so that's going to be 6, and you can see that the second one here is 12, so 6 plus 12, and that really has to happen twice. So I can write it again, or just say, let's take this whole thing and multiply by 2, and then if you want to, you know, put it in your calculator, that's totally fine. So we got 2, and then we got 1/2, and then we have a 4, and then a 6 plus 12, and all together that's going to be 72. So 72 centimeters squared for the trapezoids. Okay, now let me get rid of all that. So that was the front and the back. Now the top and the bottom are not the same size, right? The rectangle that we have on the top here is not the same size as the rectangle that we have on the bottom, because this length is not the same as this length. So I'm going to have to separate those out. So I'm going to go with the top next. 2 is going to be just the top. So this piece here, and that's just a rectangle, so it's just the length times the width, and this length is 10, and this width is 6. So the top is going to be 6 times 10, which is going to be 60 centimeters squared. Oops, squared. Okay, now I'm going to work on the bottom. Bottom's another rectangle, just a bigger one. Oops, I swear I said eraser. So 2, and then 3 is going to be the bottom here, and the bottom rectangle is 10 centimeters by 12 centimeters. So the bottom is 10 by 12, which is 120 centimeters squared. So I got the front and the back, I got the top and the bottom, and the only pieces that are remaining now are these side pieces, and these are the same, right? I have a rectangle here that is 5 by 10, and then I've got the same 5 by 10 rectangle on the other side. So I have the side rectangles as my fourth areas. So the sides, and there are 2 of them, are 5 by 10. So 5 by 10, 5 by 10, that's 50 and 50, or just multiply by 2, and that makes 100. So now the total surface area adds all of those together. Now I've got, let's see, just make sure I accounted for everything, right? 1, 2, 3, 4, 5, 6 surfaces. And if I look at this thing uncluttered from my highlighter, do I have 6 surfaces? 1, 2, 3, 4, 5, 6. Yep, all 6 surfaces accounted for. Okay, so now let's add all these up. We've got 72, 60, 120, and 100. So this surface area is going to be, let's see, that's 220, 280, 352, but let me not chance anything here. Let's see, 72 and 60 and 120 and 100 is, yep, 352. So 352 centimeters squared. Okay, there it is. Now I think you'll see two similar to that in your homework. Now, volume is a bit of a different story. Surface area, if you wanted to Google, there are some formulas. I don't know that they're any easier to use. I like to piece it out, but if you want to look at formulas, you're welcome to. You're only going to have like 2 problems in your homework regarding surface area though. Volume, however, is a little more complicated, and so we're going to have some formulas that we're going to stick to calculate those volumes. Now, what are we talking about with volume? The volume for a 3D figure refers to the space that is enclosed by, or the space that is inside of your 3D figure. So if you enclose the space with a 3D figure, how much fits, you know, what could you fit inside of that 3D figure, or the space inside, we call the volume. And the units for volume are cubed. So units for area were squared, units for volume are going to be cubed, and that should make sense when you look at something like the rectangular prism, right? Now you have a length and a width and a height. So if you multiply centimeters times centimeters times centimeters, you're going to get centimeters cubed. Now the units are just units. They don't do anything to your work or your answer. So it's just to know that the units should be cubed, okay? So these are common formulas here, not every formula possible, but I don't think you're going to see anything outside of these. So obviously V represents volume. B and H we've talked about before, base and height. Now we have, if you notice here in this triangular prism, we have this L. That's technically it's like a version of height, but when you're dealing with a triangle with a base and it already has a height in it, they just want to stick in another variable so we don't confuse the things. But you can see in the picture, you want the base and the height for the triangle, and then this height is for the entire figure, okay? For this cylinder, we've got pi, radius, squared, and height, and same variables everywhere else. I don't think there's anything different. So the only new variable that you see is L, which is just the height for this entire figure versus the height for just the triangle. Okay, so let's try to use a couple of these. So for number 3, this is a rectangular prism, and the volume says just multiply length and width and height. So the length and the width and the height, and it doesn't matter what is what, just make sure that they're all separated. So I'm going to call this the length and the width and the height. Although if you mix those around, it doesn't matter as long as you're not using one measurement more than once, right? Make sure all 3 are captured in there. So this volume is length times width times height. So 3 centimeters times 4 centimeters times 5 centimeters. So again, centimeters times centimeters times centimeters gives me my centimeters cubed. And then 3 times 4 is 12, and 12 times 5 is 60. So this volume would be 60 centimeters cubed, or we could say cubic centimeters. Now, just like before, when you're doing your work, if you don't want to write the centimeters in there every time, you don't have to. Just make sure you get your units in there at the end. Okay? So let's try that again. Number 4, we've got a cylinder. And for a cylinder, it says pi times radius squared times height. So the volume for this cylinder is going to be pi times radius squared times height. So pi times the radius, be careful. If our diameter here is 12, that's all the way across is 12, that means the radius is going to be 6. So we're going to put 6 squared in here, and then we're going to multiply by the height. The height is here, 4 feet. So put that in there, and then our volume is going to be equal to 6 squared times 4. So 6 squared times 4 is going to be 144 pi, right? The 6 squared times 4 is 144. There's still a pi in there, and then we're going to call this feet cubed. That's the exact volume, right? And I think most of the time that's preferred. However, if we wanted the approximate, then we would just take that and multiply by pi. So if we multiply by 3.14, then we're going to get 452.16. So approximately 452.16 feet cubed would be the approximated answer. All right, number 5, we've got a cone. So the cone, or we call that a circular pyramid, it says pi r squared h divided by 3. Pi r squared h divided by 3. So volume equals pi r squared h divided by 3. And so in this case, pi times our radius is 4, that gets squared, and then we have to multiply by the height. Small problem. Now, some of you might have been wanting to plug the 5 in there for the height, but when you measure the height of something, do you measure sideways like this? Absolutely not. The height for the triangle is from the top straight down to the bottom. That's how you would measure your own height, right? So we're missing that dimension. How do we find that missing dimension? Hopefully we know. This is like the 3rd day in a row. If I need to figure out what this height is, I can use the Pythagorean theorem, right? The height squared plus 4 squared has to equal 5 squared. So that's going to be 16 and 25. If we subtract that 16 over, then we have h squared equal to 9, which means that height is going to be 3. So our height is 3 centimeters. And so that's what we're going to plug in here for our height. And then we're going to divide by 3. So volume is going to equal, well, these 3's are going to cancel. You can put this in your calculator if you want. If you were going to put this in the calculator to get your exact answer, don't put the pi in there yet. You would put the 4 squared times the 3 and then all over 3. And you're going to get 16. And see if the 3's cancel, all you have is a 4 squared, which is a 16. So this is going to be 16 pi centimeters cubed exactly. And then if you wanted to approximate it, then the pi is going to have to go back in there. So then if we take the 16 and multiply by 3.14, 50.24 is our approximate volume. Okay, last one is a sphere. Feel free to give it a shot if you want to pause the video. Volume for a sphere is 4/3 times pi times radius cubed. 4/3 times pi times radius cubed. Sorry, bouncing all over the place here. So 4/3 times pi and radius cubed. So in this case, 4/3 times pi times, again, this is a diameter of 12. All the way across here is the same as all the way across here. So if our diameter is 12, again, our radius is going to be 6. So we're going to put 6 cubed in here. So volume is going to be, now to get the exact volume, let's not put pi in the calculator, just the 4/3 and the 6 cubed. So 4/3 and then 6 cubed. And I don't think oops. Goodness. Fat fingers. I don't think I need parentheses around the 6 cubed, but just to be safe, yeah, 288, we're good. So this is going to be exactly 288 pi centimeters cubed. And then if we want the approximate answer, then we'll put the pi in there. So 288 times 3.14 is 904.32. So 904.32 centimeters cubed for that approximate. Now I know I didn't run through all of the formulas, but it's really just using a formula, so hopefully you'll be okay. But if you run into any issues, then just give me an email and I'll get back to you as soon as I can. This is the last one for the week. Let's see. Next week on Monday, we're going to be actually wrapping up Chapter 10. We're going to look at some more surface area and volume, but in some applications, some word problems. It won't be too bad, I promise. But that will be it, I believe, for the unit. If there's, I had to look at the calendar again, but possibly 1-2 sections left. So there's going to be a quiz coming up next week. When you get to it, it will be taken just like the midterm was. So it's in Canvas, and you'll have all your notes.